Hi everyone, it's Mr. Baker here with another physics video. Today we're going to be looking at satellites and orbits. So today we're going to be looking at satellites and orbits, and we're going to be answering this question: why do the planets orbit the sun at different speeds? Okay, so I've got a bucket of water. Okay, so I'm going to whiz this around my head. Oi!
What? It didn't get you wet.
Okay, right, we're going to do it again, but this time I'm going to stop it above my head. So in the demonstration you just saw, it seems as if the water in the bucket is defying gravity whilst it was being spun around my head. But is it really? No. Gravity, the force pulling down on everything, is still at work even when the bucket and water are above your head. The water's inertia wants to keep the water travelling in a straight path, but gravity is acting on the water, causing it to fall in a downward path that will eventually hit the earth. However, while the water is falling, the bucket is falling with it, catching the water. What keeps the bucket and water moving in a nice circular path that doesn't get wet or messy is force provided by the string. The string acts as the force that pulls the bucket and water towards the centre of the circular path and keeps them from following their paths of inertia, giving the illusion that centrifugal force is pulling the water away from the centre. You also saw that in order for the bucket to keep falling with the water, the bucket must travel fast enough to keep up with the water. As you saw, if you spin the bucket too slowly, the water will fall out and you'll get wet. What would happen if the bucket was spun too quickly? Well, in this diagram, we've got a bucket on a string. If it was spun too quickly, then you could probably expect that the string would snap. What direction would the bucket fly off? Well, you might think that it would go in a circular path and carry on, but actually the inertia would carry it off in a straight line. So let's have a look at these questions then. We've got the moon travelling around the Earth, orbiting around the Earth here. So is the moon at rest? No, it's going at a constant speed. Is the moon travelling in a straight line? No again. So although the speed is constant, the velocity isn't. The velocity is changing because the direction is changing. If the velocity is changing, then it must be accelerating. Newton's second law tells us that objects that are accelerating must have a resultant force acting on them. And that's basically what conclusion we can come up with. So if it's accelerating, then it must have a force. And this force is the thing that keeps things travelling in a circular path. Since velocity is speed in a given direction, if an object is travelling at a constant speed but constantly changing direction, it must be accelerating. This is what's happening in circular motion. The acceleration is called centripetal acceleration. Centripetal comes from the Latin meaning centre seeking. Centra, centre, petal or petal, seeking. A circle follows a curve all the way round, and we can describe it quantitatively as well as qualitatively. Quantitatively means with numbers, qualitatively means with words. All objects that follow a curved path must have force acting towards the centre of that curve. We call this force the centripetal force. So we've got the centripetal acceleration, and that must have a centripetal force. Objects moving in a circular motion have a resultant force acting on them, even if you can't see the force. What force acts on the natural satellite, the moon? Well, in this case, it's gravity. So we've said that all objects orbit the Earth are called satellites. There are two types of satellites, natural ones and artificial or man-made ones. Okay, so here we've got a little simulation that shows us circular motion. The washers on the bottom will be a certain force that we have got as our centripetal force that's pulling this round in a circle. We've got a radius here, 200 centimetres is the radius of the circle, and we've got a mass on the end which is 25 grams. So let's just have a look and see what happens. So you can see we swirl it around and it goes around in the circular path. Okay, so what we're going to do is we're going to change the force, the mass and the radius and see how that affects the time it takes for us to complete one circular path. Okay, so we'll do it by measuring 5 spins and then dividing by 5 to work out the time period. So let's start here, let's go. 1, 2, 3, 4, 5. Okay, so just a little bit more than that, wasn't it? But so that was, let's say, 8.6 seconds. Okay, so for one spin round then, the time period would be 1.72 seconds. What I've done there is I've gone 8.6 divided by 5, and that equals 1.72 seconds. Okay, so let's reset it. And let's increase the centripetal force. I'll increase the centripetal force by adding the number of washers on here. So let's add a few more. So by having a larger centripetal force, what's that going to do to our time period? Okay, so let's do the same thing again. So we'll do 5 spins round and we'll count those. 1, 2, 3, 4, 5. Okay, so I wasn't very accurate again, but because we're doing 5, hopefully that'll average out. Our elapsed time was 5 seconds this time. So 5 divided by 5. Our time period here is going to be 1 second. So when we had 7 washers on there, it was 1.72 seconds. And now we've got 21 washers on there, and it's 1 second. So when you increase the centripetal force, you increase the orbital speed, and so the time period, the time for one orbit, decreases. Okay, so now I'm going to decrease the radius. Let's make the radius just over half there. Let's do the same thing again. We'll count 5 times round. 1, 2, 3, 4, 5. Okay, so we've gone back to having 7 washers again. Remember, when it was at 200 centimeters, the radius with 7 washers, our time period was 1.72 seconds. We've just done just over, well, just about 100 centimeters, so about half. And what we've got 6.3 seconds for 5 times round. So the time period this time was 1.26 seconds. So when you reduce the radius, you reduce the time period. The last thing we can change then is the mass. So let's increase the mass. And let's do the same thing again. So remember, the first time round was 1.72. Let's see what it will be now. 1, 2, 3, 4. You're still awake? 5. Oh, look at that. So 5. So now we've got 20.9 seconds. Okay, so 20.9 seconds for 5 times round. So that is 4.18 seconds for one time period. Originally it was 1.72. So when you increase the mass, then you increase the time period. We've seen that orbital speed depends on the force. In our solar system, it falls as the strength of gravity falls at greater distances. This is inversely proportional to the square of the distance. On the x-axis here, you can see that I've got the radius of different planetary orbits. And on the y-axis, I've got the orbital speeds. Now, the radius is measured in AU, which is astronomical units. 1 astronomical unit is the distance from the Earth to the Sun, which is about 150 million kilometres. The speed here is measured in kilometres per second. So Earth is at 1 AU, 1 astronomical unit, and travels at a speed of about 29 kilometres per second. Saturn is at 9.5 AU and travels at a speed of just over 9.5 kilometres per second. So you can see that the orbital speed decreases because of the distance that the planet is away from the Sun. So let's have a look at some satellites, some artificial satellites then. So here we've got a polar orbit. Polar orbits take the satellites over the Earth's poles. They're used for monitoring the weather, military applications like spying, and taking images of the Earth's surface. The satellites travel very close to the Earth, as low as 200 kilometres above the sea level. So they must travel at very high speeds, nearly 8,000 metres per second. Geostationary satellites take 24 hours to orbit the Earth, so the satellite appears to remain the same part of the sky when viewed from the ground. Satellites in geostationary orbits are used for communications and satellite TV. These orbits are much higher than polar orbits, about 36,000 kilometres, so the satellites travel more slowly, at around about 3 kilometres per second. For a geostationary satellite to appear like it is stationary above the point of the equator, it must orbit at exactly the same angular speed as the Earth rotates. As we have seen, the speed of an object in circular motion depends on the force on it, and that is why it must be at 36,000 kilometres above sea level. Okay, so that's the end of this lesson on satellites and orbits. These are the things you should be able to do. You should be able to compare and describe the orbits of planets, moons and artificial satellites, list some uses of artificial satellites, describe the different types of orbits of satellites, and describe the forces acting on an object that cause it to travel in a circular path. You should be able to explain why a centripetal force can change the velocity of an object without changing its speed, and explain why a geostationary satellite must be a specific distance from the centre of the Earth. Okay, so at the beginning we asked this question then: why do the planets orbit the Sun at different speeds? The speed of an object in circular motion depends on its radius, its mass, and its centripetal force. The main reason a planet's orbital speed changes is because of how far it is away from the Sun. The closer a planet is to the Sun, the stronger the Sun's gravitational pull on it, and the faster the planet will move. The further away it is, the weaker the Sun's gravitational pull, which is its centripetal force, and so the slower it will move. Okay, so that's been our lesson on satellites and orbits. I've been Mr. Baker, and this has been a physics video, and I will see you next time. Thanks very much.